All right, so I'd like to demo my central dogma hands-on activity that I've created. So what I have here is a gene. It's a segment of DNA that codes for a protein. Quotes because it's not a real protein. We've got it anti-parallel, so there are two strands running anti-parallel. I've labeled one the template strand and one the coding strand so that we know which one to use to make our mRNA transcript. And the ribbons, which I don't have enough of on this molecule, are supposed to represent the hydrogen bonds. So if I had the time and the inclination, I would have 2 ribbons connecting each T and A pair, and I would have 3 ribbons connecting each CG pair. Notice that these strands are complementary to each other. They're anti-parallel and complementary. And I've color-coded the 4 bases just for fun, for visual effect. So in order to start transcription, we first have to separate these 2 strands of DNA by disrupting those hydrogen bonds. And the enzyme that does that is helicase. That's the amoeba sisters animation of helicase, and I've attached them to some scissors because the helicase is going to come through. See if I can do this with my left hand. And it's going to unzip the DNA. I can't, so I'll just do it this way. By disrupting those hydrogen bonds. So here comes helicase, and we have separated our 2 strands of DNA. Now, when we are making our mRNA transcript, and this piece of paper here that says mRNA, all right, also you can see that it has some double-sided tape on here, and we are going to do transcription. Now, to do transcription, we want to use the template strand of the DNA. That's because the coding strand has really the sequence. We just need to replace all the T's with U's. And so since DNA and RNA are built using the complementary base pairing rules, we need to use sort of the opposite strand. So the template's the strand that's opposite the coding strand. So that's why we call it the template strand, because it's our template for transcription. So transcription is going to be done by this enzyme here, the RNA polymerase, and I've taped him to some tweezers. He's going to pluck out the RNA nucleotides from pool of nucleotides and build our strand, our new strand of mRNA. So this is sort of a team activity. It's nice to have one person who's sort of plucking and then another person who's sticking. So make sure you're following the base pairing rules. So T on the DNA is going to base pair with A, an RNA A. A corresponds with U on RNA. So there is no thymine in RNA. There's U instead of T. So the good mnemonic for remembering the base pairing rules that I like, that's also from Amoeba Sisters, is apples in the tree, A binds with T, car in the garage, C and G. And then you just have to find a way to remember that U replaces T in the RNA. So while I'm doing this, and I should be using my RNA polymerase here, again, this will be a really good activity for 2 people to work on together. I'm going to talk a little bit about some other differences between RNA and DNA. So RNA is ribonucleic acid, and it's called that because it uses the sugar ribose. All nucleotides, these letters, which I've simplified here as just little blocks, but in real life are actually molecules that are made of a sugar, a nitrogenous base, and a phosphate. And the sugar of RNA is ribose, while the sugar of DNA is deoxyribose. I want to keep going here, but this is going to be a really long video if I do that. So essentially, I'm just going to do part of it. So I've made part of my mRNA transcript here. All right, and it will be the full length of this strip by the time you're done. All right, and once you've made the mRNA transcript, transcription is done, and now it's time to translate. It's time to translate our mRNA sequence into protein. One thing to note about this strip is I've made it out of paper, and these RNA nucleotides are just paper. But the DNA is laminated paper, so it's thicker, it's more durable, it's more long-lasting, and I did that on purpose to represent the fact that DNA is a more stable molecule than RNA. At the end of the process of transcription, we will dispose of this disposable fragile strip of paper, because that's what happens in the cells. So then, once transcription is over, we're going to pull out the materials for translation. We have several tRNAs with their anticodons and a piece of Velcro at the top to charge them with amino acids. And we have a pool of amino acids here that also have Velcro. And somewhere in this pile, I have my ribosome. So translation happens at the ribosome. So I'm just going to stick my RNA on top of the ribosome here. Oops, still sticky. And then we're going to go through a process of, first we need to charge our tRNAs. So in order to do that, there's a cheat on the back side of it. Tells you which amino acid to charge it with. In this case, it's a stop codon, so I'm going to charge it with the stop sign. All right, where's another one? Here's one. Its amino acid is histidine. So I'm going to dig in this bag here and look for an amino acid that says histidine, which has a little piece of Velcro on it. And I'm going to stick it right here. Ta-da! So now I have a charged tRNA. All right, once all of your tRNAs are charged, all right, you'll lay them out, and then you'll start a process of matching them to your codons on the transcript here. So the mRNA, I'll flip this so you can see it correctly. The mRNA letters are arranged in triplets that we call codons. So the first codon here is AUG. So we need to find a tRNA that's complementary to AUG. So the complement would be UAC. So we're looking one that says UAC, and that would be this guy here. I guess I should charge it. Need to have some of these charged. All right, so UAC is my first tRNA, so it's going to go here. And then my second one, CUU, the complement to that would be GAA. So I'm looking for one that says GAA, and that one needs to be charged with a leucine. So let's get that charged. This is not the greatest video here. Don't quite have all my ducks in a row. Alrighty, there we go. Now our tRNA is charged. Okay, so it's going to bond here. And then what's going to happen is a peptide bond is going to form between these two amino acids here. And I'm going to use some tape, just some Scotch tape. I'm going to take this methionine and tape it to our leucine. And then this tRNA is going to exit. Our ribosome moves along. And we will continue to do this. So we'll continue to read our codons, bring in new tRNAs that are charged with amino acids, and then tape the amino acids together so that we build this growing polypeptide chain. So by the time we get to the end, we will have a chain of amino acids that are all taped together, the tape representing the peptide bonds holding the amino acids together. And when that is done, we will have our polypeptide, and we will take our mRNA, and we can just tear it up and throw it away, because that is what happens in our cells after we make proteins from mRNA transcripts. And that is the transcription, translation, central dogma demo.